Lecture 2, Rust Basics. Rather than just tell you, go off and learn Rust on your own, we will spend some time on the subject. So we'll tell you about important features, we'll tell you why and how they support the goal of programming for performance. It would not make sense to introduce a new programming language at this point, even though we do have high expectations in terms of your programming ability in this course, and just think that, oh yes, go off and read the documentation without any instruction. I don't think that would be fair. So we're going to dedicate some time to this very topic. Now, one of the things that I have to point out is that reading the documentation, watching a video about a programming language, reading the lecture notes, anything like that, isn't necessarily super effective in terms of actually learning a language. I think there's no substitute for actually writing code in the language. I mean, there is a place for doing some research, reading about the documentation of the language, understanding its core concepts. I think there is a place for this lecture, and that it will help you in terms of understanding what is going on in Rust, understanding why certain things matter. But like I said, there's no actual substitute for trying to learn the language. So with that in mind, we have prepared some practice exercises. The practice exercises are very easy, I think, anyway. They're trivial, really, but they're a way to understand the language, get familiar with the tooling, get going, get started, practice with it, and get a little bit of hands-on experience. If you ask me anyway, you probably can't learn to swim just by watching a video. I mean, instruction is an important part of learning to swim. The teacher, the lifeguard, what have you, will give you some information. They will tell you certain things. You may practice a little bit, but there's no substitute for actually getting in the water and swimming. And the same is true with learning this language. So a little bit of goal setting before we go on. And I want to specifically exclude some things that are just simply not in here. We're not going to talk about them. They're not in scope for what we're going to teach, but they're important nevertheless. So we're not covering the very basics of Rust. I'm not going to talk too much about this is how you write an if statement, and this is how you create a for loop, and these concepts we imagine are familiar to you from previous C language or C-like language experience, and it would be a waste of time to focus too much on that kind of thing. It will be better, I think, where we focus on what is important for this course. So what are the concepts that matter, and what impact they have in terms of programming for performance. And then, with those things in mind, then we will go on. When we are working through a particular subject, I mean, we will encounter syntax for things that we don't necessarily know. So we will encounter how to write a while loop equivalent in this language. Okay, that's fine. We might make mention of it in passing. When it comes to return types for functions, I'll talk about it. But we're going to focus on what is important here and not get bogged down or sidetracked in stuff like how to print to the console. If we encounter a new piece of syntax, I will probably explain it. If not, the official documentation is actually pretty good for Rust, so reading it would not be a waste of your time if you were going to look up something in particular. The material in this lecture is mostly based off said official Rust documentation combined with personal experiences, mine and others, which hopefully we combine to give you a good overview of things that are important and that we need in this course. Okay, now one of the things that we'll point out is in semicolons usage. Previously, C, C++, Java, all statements end with a semicolon. In other languages like Kotlin, semicolons are optional but don't do anything. In Rust, it is not the case. Semicolons separate expressions. And so the last expression in a function is its return value. So looking at the example down towards the bottom, we see function return a number. A function is denoted with fn at the beginning. So this is the keyword that says function. We have a name. We have a little arrow, and the arrow then specifies the return type. And U32 is an unsigned 32-bit integer. And we do an assignment statement. Let x is assigned 42. So the let keyword is used in assignment. And then the last statement is just x plus 17. And this is an expression, so it takes 42 and adds 17, and that is in fact the return value. So anywhere that you see this kind of block in a function is one place, but you can also have it like in an if statement. You can assign the result of an if statement. For example, anytime you have these curly braces, you can usually use the last statement in it as a return value. If that seems weird to you and you don't like it and you prefer explicit return, by all means, use it. And you use return in other situations where you want to exit early from a function or something like that. And that is no big deal. You just do it. You return exactly as though it were C or C++. You'll see there are examples of both in some of the code that we're going to write. Either one is acceptable. Which one is allowed in your live in production industry code is a matter of what is your coding convention, so remember to follow that. Now, change is painful. Variables in Rust are, by default, immutable. This might make you question, wait, why is it called a variable if it doesn't change? But a variable is a concept we're familiar with from a programming language, and variables can change their value, but by default, they are immutable. Immutability is really good in terms of performance. It helps the compiler to reason about whether or not a race condition may exist. So in the example that we're looking at here, let x is assigned 42. You'll notice we don't specify a type. When no type is specified, the compiler will try to infer one. If it can do so, then it will be fine. Your editor might show some hints saying, okay, we've inferred that this is of type i32 here, so an integer of 32 bits. And then a later attempt to assign it is a compile time error. Why? Well, this is because we've declared a variable, and the variable is, per default, immutable. And the compiler wants that for the purposes of reasoning about race conditions. If there are no writes to a particular variable, race conditions can't happen. You remember, I hope, from our earlier discussion, that a race condition occurs when there are multiple concurrent accesses to a variable, at least one of which is a write. No writes, no race condition. That's pretty good. That's desirable. If you don't believe me, here's an example of something in C where this could go wrong, and you can do the same thing in Java and get the same result. If my pointer is not null, then size is my pointer, and dereference it and get the length property, and a segmentation fault occurs. And you're like, well, why did this happen? We checked if my pointer was null. It is not null. What dark magic, what trickery has occurred here? And this is a real problem, and this does actually happen. Most of the time, we would be fine. However, if another thread or an interrupt, a signal, something that ran asynchronously, were to run and change the value of my pointer, maybe set it to 0, so set it to null, after the if check has occurred, but before the dereference occurs on the next line, we would have a segmentation fault, and it would be difficult to guard against because we already have a guard. We have a null check that surrounds this dereference, but it's not enough because my pointer got changed by something else. This kind of thing has occurred to me actually in production Java code, and you can put all the if not null blocks if you want, but it won't help in this scenario. You would actually have to use locks. I'll hedge a bit. Rust prevents data races on shared memory locations, but not all possible race conditions everywhere. You can still race on a file system if for example, you are expecting some external behavior. In this case, if my pointer is a global pointer, it has to be immutable. We don't have to do this but there do exist other types like atomic pointer, and you can get races on atomic types, as we'll see later on, again, if you haven't seen that previously in a concurrency course, because a read individually might be atomic, but a pair of them is not necessarily so. Anyway, if things can change out from under you, that's bad. Immutability in Rust is kind of forever. The compiler doesn't let you make changes to something via trickery. There's a not nice thing you can do in C where you have a const variable and you want to change it. Well, you just say, oh, I take address of it and change it through a pointer, and the compiler says, okay, I guess so. I don't see anything wrong with this. Not cool, man. Not cool. However, Rust grudgingly permits dark magic. You have to brand your code with the unsafe keyword, and you have to accept the risk that there will be unsafe, undefined behavior risks. The unsafe behavior defeats at least some of the point of Rust. You'll see when we actually talk about unsafe when you need it, what it's for, and why it's important. But broadly speaking, this superpower, if you will, or this dangerous, dark, evil thing is not something you want to use if you can help it. Sometimes you have no choice. All right, now listen, you do have valid use cases for things to be mutable, and you may have been screaming at me for the last 5 minutes or writing furiously in the comments, how can you make a programming language where you can never change a variable? That's not the case. I just said that it's by default immutable. And ultimately, if you want something to be mutable, you just have to declare it as such so that it is acknowledged that this is what's happening. Now, to declare it as mutable, you just add this extra keyword, mute, to the definition, like let mute x is assigned 42, and that means that this variable is mutable, so later if you want to assign x is assigned 0, that's perfectly fine. Generally speaking, our advice, not speaking for the Rust language here, but just in the context of this course, is you want to minimize the number of times where you use mutability. Mutability is, like I said, potentially a risk in terms of race conditions and things like that, and ultimately it is better to be immutable if you can be. There are valid scenarios for using mutation, of course. It might be a lot clearer to write your code so that you are mutating a count every time. For a sufficiently large or complicated object, it's faster to change the one that you have than make a copy that's different and then just replace the original with the new copy. Write the best code for your situation. Obviously, guidance like immutable is better than mutable is just like, broadly speaking, we think this is the case. It is not a hard rule where it's always better. You should write the best code for the situation that you're in. Just keep in mind that when you are making something mutable, Rust requires you to make that explicit. You are openly acknowledging that this could change, and it has the compiler check your work. What do I mean by check your work? The compiler then has to validate that there aren't concurrent accesses to this mutable data that conflict in some way. So there is some extra work for the compiler to do. I mean, you don't care. The compiler doesn't charge you a fee for this, but it does have to consider carefully when change is necessary if it's done correctly. Then there are constants, and constants are not quite the same thing as global variables. Constants are immutable and immortal. That is, they never change, and they are valid throughout the entire lifetime of your program. So if you want to define the speed of light in meters per second as a 32-bit integer, const is the keyword, then speed of light in meters per second is equal to 299,792,458, something like that. Constants don't really exist at runtime, and they don't have an address. This prevents you from doing all kinds of really dark things that we do in C, where we take addresses to global variables or that kind of thing. You can't in Rust. It doesn't have an address. Does it even exist? This has gotten very metaphysical. It still has an effect in your program. When I say it doesn't exist, it wouldn't be the case if you multiplied, E equals mc squared. The c component would somehow fail to materialize. However, they aren't treated the same as other variables. Rust also has global variables defined using static. Although those things themselves are immutable, they can point to things that mutate. The standard warning about global variables is they can be accessed from anywhere, and it's not necessarily very good program design to have a lot of those in your code. So it is perhaps ideal to minimize global variables altogether. In previous courses, and I'm also guilty of this in something like ECE 254 or 252, if you've taken it from me, you will know that sometimes in an assignment, an exam question, we set up some things as global variables, mutex lock or something, because we are trying to write a small amount of code that's really about using threads correctly or synchronizing the action of various threads, and not really about passing data around from one thread to another in terms of, here's the lock and here's the shared buffer and those things. Rust really discourages that, and it's good advice. It's a lot easier to pass data around in Rust, and you should use that instead of global variables. There's, again, some temptation to do that in a simple program that's, here's an assignment that we're doing in a course. It's throwaway code because you write it, the TA evaluates it, and then it's never seen or heard from again. But because it's easier in Rust to pass this data around as we should, we really encourage you to actually pass data properly and not just allocate things as global variables because it would be easier. And then there is shadowing. And shadowing is intended to address a problem of what do I name things. So here's an example from the docs where you read in a guess into a string variable. We'll see here. So we're going to create guess as a new string using the constructor. So string is the class, then we have what in C++ is the scope resolution operator, and then the function new. And this function instantiates a new string. Then we are going to read a line in to this guess, and we'll see this expect notation. And expect says basically if something went wrong, then we throw an error. And the error, in this case, contains the text failed to read line, so we can see what went wrong. We'll talk about the error handling shortly, but just know for now that that's error handling. We are explicitly acknowledging the possibility that reading a line could fail. And then we're going to convert the guess into an integer, and to do that we trim it, so cut off any excess white space that we don't need, try to parse it to an integer. If that succeeds, we assign the value to a variable guess of type unsigned integer 32 bits, again with expect in case something goes wrong. The idea here is that we don't have to call them like guess and then guess parsed, anything like that. There are realistically two variables. One's a string and one's an integer. They just happen to have the same name. And using the new one, like creating the new one, guess, as an integer, is replacing, if you will, the previous. The previous string can no longer be used. It's good to know. So you don't have two things named the same thing, which you don't want. But it saves us from calling them guess and guess parsed or something, or guess int, which we could potentially get wrong, which, again, maybe that would be bad. Maybe we don't want that. So it's better to use shadowing to reduce the amount of what do I name this kind of conflicts. Now, we got to talk about memory management. So in languages like C, memory management is, well, manual. You allocate and you deallocate memory using explicit calls. And these explicit calls are malloc and free, or new and delete, that kind of thing. Those we are broadly familiar with, I imagine. Now, in other languages, it's partly manual. You explicitly allocate memory in that you use the constructor, you create it, use the new keyword, that sort of thing. But deallocation takes place using garbage collection. So every time we create something, we are effectively creating it explicitly, but garbage collection occurs when the Java runtime can figure out that this memory is no longer needed. So it can be thrown away at that point, which results in it being collected as garbage whenever the garbage collector feels like it's going to run. Okay, that's a strategy. It does... garbage collection does deal with some problems that have probably plagued you in C code that you've written, such as failing to deallocate things or forgetting or anything like that. But C++ has a memory management strategy, RAII, which resource acquisition is instantiation, and Rust does the same. But because this is a core design feature of Rust, it does so at compile time with guarantees through the concept of ownership about how things are supposed to work. In C++, if you follow the pattern correctly and you do what you're supposed to do, you get the right behavior. But in Rust, you have to do it the right way. There's no opting out of it. There's no, I accidentally used the wrong thing. There's no trickery to get around it. So you might be thinking, before we go on, what's wrong with garbage collection for this purpose? So the real answer is, well, the magic word, performance. To have garbage collection, we have two things. We have a runtime, and there is an actual cost of collecting the garbage. Okay, let's start there. The runtime is the Java runtime environment, and it's not free. It does take CPU cycles for the Java runtime to do its thing. Any JVM language has a runtime. It, at runtime, keeps track of the memory that's been allocated, decides when to run the garbage collector, all of that. There's actually a lot of things that the JRE does, but whatever it does comes at some performance penalty because it takes CPU cycles to do what it's going to do. The other thing, of course, is actually collecting the garbage. And one of the things that's a little painful about Java is the garbage collector can run whenever it wants and take as long as it likes. That can be annoying if there are certain guarantees that you are trying to make in terms of, I would like to respond to events within a certain fixed period of time. Well, if the garbage collector has decided now is not a good time, there's not very much you can do about it. You are going to have to wait for the garbage collector to actually take its time and do it. Now, the newest Java garbage collector is the G1 garbage collector, and it is rather complicated, but interesting if you're into this kind of thing. It has a concurrent phase which runs alongside your application and just picks up simple trash. And then there is a parallel phase which runs in a different thread, and it may stop the world. That is, cease execution for all your threads, and then analyze what's garbage and what to keep and what's supposed to go away. Now, the G1 garbage collector provides probabilistic guarantees on pause time, so it's not quite as dire as it takes as long as it feels like. But still, the garbage collector can't necessarily promise a specific time frame. And so, yeah, the downside of that is it is a little bit unpredictable. Now, garbage collection, you might be thinking. Luxury. Klingons manage their memory manually. Debug. Klingon programmers do not coddle the weak. Yeah, I mean, you can take that approach. I don't know that I would want to ride into battle on a Klingon warbird if this is how Klingon programmers write their code. Because the idea that it's like hard and it should be hard and we are Klingon is, I don't think, like great in terms of actually producing working software such that people can use it and rely on it. if you choose to write your code in C or C++, like just for the extra difficulty, because you're like, yeah, it's really show-offy to do a hard thing for no reason, I mean, I can't stop you. But I don't know many companies that would support that kind of thinking. They probably want the code written in the most efficient way possible. Well, whatever gets the feature shipped, whatever gets your MVP launched. The truth of the matter is it's hard to get C and C++ right. Your C or C++ code is probably wrong. Mine is, anyway. I would prefer not to judge C code or C++ code more than is necessary. And all the extra work that it takes to verify that your code is correct, all the runs you do with Valgrind, all the static analysis tools, all of the extra steps and audits and what have you are time, effort, and money that could go elsewhere. If you could offset some of those costs, if you could avoid some of those costs, if you could push them to compile time when they are less expensive instead of at runtime when they are more expensive, that's better. You can get more done. You save the company money. It is the ideal. So, yeah, I mean, when you are writing your C or C++ code, you're not paying garbage collection costs, but there is the cost of manually managing memory, and that cost does include bugs, which can be expensive to fix, not only in programmer time, but also if something goes wrong. And you have to clean up the corrupted data from your database or something. That's hard. So to dispel another myth, Rust is not necessarily better in terms of performance than C++. In general, if you are writing your C++ well and you're writing your Rust well, we expect that their performance is likely comparable. The difficulty, of course, is it's harder to get the C and C++ code right. So, with that in mind, we can now go on to the concept of ownership. Now, Rust has a concept of ownership. It is not the only language that has ever had such a thing, because as we've seen, C++ has a concept like this. But Rust is strongly distinguished from a lot of other programming languages based on this strategy. And it uses ownership as the memory management strategy. Ownership has lots of applications, and things that are interesting to us right now are the ideas of memory management and safe concurrency. So the compiler can determine, at compile time, obviously, when allocated memory can be cleaned up. There's a little complication to that in that deallocation might be compile time conditional in that the compiler inserts some code specifically saying when to deallocate it. That's fine, but it makes a determination of when this should happen. And memory can be cleaned up when nobody needs it anymore. Contrast this against what happens with Java. In Java, you are writing some code, it allocates memory, and then when that memory no longer has any valid references to it, so it's gone out of scope, that memory hangs around until the garbage collector sees fit to come and clean it up. That's not what happens in Rust. In Rust, when we've figured out that it's no longer needed, we can get rid of it immediately. The compiler will insert code that says, okay, the owner of this memory has gone out of scope, trash it. In the trash it goes, and however much memory it was, that gets deallocated, and we don't have to wait, and it doesn't hang around until the garbage collector decides, okay, it's going to collect that memory. Now, ownership imposes restrictions on how your code is written. There will inevitably be moments where you curse at the compiler for not letting you do what you want, and more than once, especially when I was getting started with Rust, I could relate pretty hard to the rage face on this, because why doesn't this work? Why shouldn't this be allowed? What is wrong here? The compiler is only trying to help, I promise. The compiler is pretty strict about stuff. It is interested in making sure that you write code that doesn't leak memory and doesn't have race conditions and things like that. And so it is strict, but for your benefit. It is going to say, look, I think that this is unsafe, or I think this is not going to work, and you will find it frustrating, I think, in the beginning, trying to work with it. But the compiler gives you some pretty good suggestions about what you should do to resolve a particular problem, with one exception that we'll come to in a little bit. There's one case where I think the compiler leads you down the wrong path, but for the most part, it's pretty good about telling you what you need. And if you understand the concept of ownership, you will understand why the compiler is telling you what it's telling you, and you should be able to address it. So it'll be a little slow going in the beginning. It will be a little frustrating in the beginning, but you will get there. You will, before too long, feel comfortable with it. You don't have to write Rust programs for a year to get there. Even doing a few exercises and a couple assignments will probably be sufficient for you to feel comfortable with how Rust views ownership. So let's take a look at a real-world example from Discord. I imagine at least some of you have used Discord. It's kind of a chat program, voice chat. People use it when playing games, that sort of thing. There is video functionality in it, that sort of stuff. But here's a real-world example of our data, and this comes from a mention service, so like notifying people when somebody mentions their name. And in the top left corner, we see CPU percentage, and there are some pretty big spikes in CPU. The average response time also has some spikes, which seem to be correlated. And there are some spikes as well in the 95th percentile response time, which is to say, ignoring some outliers on the worst 5%. Do we also see some spikes? Yes, we do. And looking at the graph for max mentions per second, it's quite noisy, but we don't see spikes there. So if our initial theory is that, well, like these are peak times where a lot of mentions happen, that theory turns out not to be supported by this max mentions data, because it's reasonably constant. I mean, it's noisy, but the data doesn't spike very suddenly at the times when we're seeing the spikes in CPU time and in response time. So what's going wrong here? Well, garbage collector. Go is a language that does garbage collection, just as Java does, and it adds a latency spike. Rust would not have such a thing because ownership. When memory is no longer needed, you can trash it, and that's it. It's gone. C++ would also not have such a spike. It would, again, just occur in a language with this kind of garbage collection. And so the article, which is linked in the notes, is kind of worth reading. Says that they decided they were going to try it out by rewriting this service in Rust. And even with basic optimization, the Rust version performed better than the Go version. Rust in the diagram is shown in blue, and then we have Go shown in purple. We'll notice that there are occasionally a little spike here or there, but it's a lot more steady and a lot more consistent over the period of time that we are interested in. The max mentions stuff is not quite identical either, but not sufficient to account for the difference between the observed behavior. So yeah, did Rust work better in this situation than Go? Yes, it did. No spikes, lower latency, better CPU, and less memory usage. It turns out to actually be a significant improvement. So, can you use Rust in a real-world scenario? Yes, you can. Does it potentially come with some nice benefits in terms of evening out these latency spikes and things? Yes, it does. I do recommend reading the article because it does go into some more details and might answer some questions that you have about some of that information, but we don't want to get dragged too much into the details of how does this Discord service work. Just keep it in mind as an example of here's a real-world example of using Rust to improve performance of a program. Okay, so we talked about the why of ownership. I've said ownership is a memory management strategy. I've said it's important. I've said the compiler will be strict about it and it might make you mad, but I didn't tell you what the rules are. Ultimately, there are 3 rules. It's deceptively simple, and the rules are as follows, and we'll go into the rules in some more detail, but like the high-level overview. Every value has a variable that is its owner. Number 2, there can be only one owner at a time, and number 3, when the owner goes out of scope, the value is dropped. Okay, so we should note a distinction between the value itself and the variable that owns it. In a statement like let x is assigned 42, well, there's memory associated with the value 42. That memory is the value as specified in Rule 1. The owner is the variable x. When x goes out of scope, that memory can be deallocated. That's Rule 3. And variable scope rules look like the ones we should be familiar with from other C-like languages. And they are, like I said, rigidly enforced by the compiler. So if we use the curly braces for manual scoping, again, this is something I'm sure you would have covered if you took a C language course with me. Not something we do a lot of, but it does happen. So we do let s equal hello world. So the value in this is hello world. It's owned by s. We print it using the print formatter, print line with the exclamation mark because it's a macro. Exclamation mark indicates a macro and is required. And then the curly braces are used in formatting the string, and we format it with the s value. And then after s goes out of scope, its value is dropped, or as Arnold would put it, I let him go. So this is a super brief example, but it gives you an idea of the allocation versus deallocation. Memory is allocated, it exists when it needs it, and then when its owner goes out of scope, the value is dropped. Now, the same principle applies in terms of heap allocated memory. So let's say that we have a string and we're going to heap allocate the string using the string from function. And this creates a new string and populates it with the string literal that we have provided. So let s1 equal string from hello, and then we will print it. Now, the representation of a string in terms of memory looks like this. We have S1, this is the stack part, this is the owner of the value, and it has some information. It has a length, it has a capacity, because what are strings but arrays of characters, and there's also then a pointer to the heap part, which is on the right, which has an index and a value. Okay, so that's pretty good. This maybe makes it a little bit clearer to make it obvious what is the stack part, it's the S1 part on the left, and what is the heap part. And when the owner, the stack part, goes out of scope, the heap part, it results in being dropped. It's deallocated. Okay, that covers rules 1 and 3. All right, everything has an owner, and when its owner goes out of scope, it is dropped. But the second rule is interesting. The second rule said there can be only one owner at a time. The at a time is the interesting part of that, because it means, in addition to the fact that ownership is on one thing, it means ownership can be transferred. So the concept of transfer of ownership is important in Rust. What's yours is mine. So when we want to transfer some data, we're going to move it, potentially. Move semantics are about transferring ownership from one variable to another. If I give somebody a birthday present, it ceases to be mine and becomes theirs. That is a transfer of ownership. Here you go. Here is your mug with a humorous saying. That is a gift. It is a transfer of ownership, and when I do that, I no longer possess it. Some types use copy semantics instead, such as simple types. And copy semantics are great when it's cheap to do a copy, and moving would be kind of cumbersome. You will know which types do copy because basically it is simple types, stuff like integers, booleans, floating points. And if you've skipped ahead a little bit and we've talked about traits, then something that implements the copy trait has copy semantics by default. It means the size has to be known at compile time and has to be stack allocated, or at least possible for it to be stack allocated. But if that's too confusing, don't worry about it. Just some things are copyable and others move. So in this code example, let x equals 5, then it assigns 5 here to this variable, and then let y equal x. We do a copy here. We don't reassign ownership because it's a simple type, and simple type follow the copy semantics. But the simple types are the exception to the rule. When we want to do something that moves a type with a heap component like string, if we look at creating the string s1 as string from hello, and then we do let s2 equal s1, that's transfer of ownership, that's movement, that's reassigning who is the owner. It is not a copy. Rust will not, for performance reasons, automatically create a copy unless you ask explicitly. If you ask explicitly, you use clone. It says, I want to make a copy of this string so that s2 is a copy of s1. Cloning an object is potentially expensive. It involves an arbitrary amount of memory allocation and then data copying. This is important to be explicit about. The kind of thing that we see here, let s1 equal string from hello and let s2 equal s1, is something that students frequently get wrong in ECE 252. They cast a pointer to another type because they got a void pointer as an argument, and now they're casting it to an int pointer. No new heap memory was allocated. We have two pointers pointing to the same thing. That is not what happens in Rust. We do not want that behavior anyway. So here's what actually happens. When we do move semantics, the s2 variable becomes the owner of the heap allocated memory, and s1 has gone out of scope and ceases to exist effectively. If both s1 and s2 were pointing to the same heap memory, it would violate that second rule of ownership because we would have two things pointing to the heap memory at the same time, and that would not be okay. So, as Sean Connery says in Highlander, because in the end, there can be only one. I can't vouch for Highlander as being a particularly good movie, but you may find it entertaining. In any case, when we have transfer of ownership, the heap allocated memory goes to S2, and S1 is no longer valid. There's nothing wrong with the code that we show here. It's just that S1 has no use anymore after the transfer of ownership. If we tried to use it, then something would be wrong. Then it wouldn't work. To give you an example, if we tried to use S1, it would result in a compile time error because the compiler would say S1 ceased to be a thing and you can't use it anymore. So if we look at the example here in main, we let x is assigned 5, let y is assigned x. Those are simple types, they copy, and if we call some macro here, it takes x and y, that's fine because we copied it, we didn't transfer ownership. If, however, x is a vector, and vectors are declared with vec, and then in angle brackets a type, which is similar to a standard vector type as you would see in C++. It is heap allocated and has the single ownership semantics. And so when we do the statement let y is assigned x, that is a transfer of ownership. And then trying to call this macro with x and y doesn't work because x is no longer valid, and the compiler will tell you it is not okay. In fact, the compiler is very kind in that it tells you what went wrong and why. And so when you do cargo run in this scenario, it tries to run the program, but first it has to compile it. Compilation fails. because we broke one of the rules, so things are not okay. So we didn't even run the program. This is just compile time error. So compiling this results in an error. So it points out to you that on line 6, move occurs because x has type standard vector of unsigned 32-bit integer, which does not implement the copy trait. So it tells you why the move occurred, because that's the way the type is set up. Then on line 7, it tells you the value was moved here. So that's where the actual assignment statement does the move. And then on line 8, that's where we attempt to use the value that's no longer valid. So that is 1,000 times more helpful than usually you get from a compiler. Usually the compiler would just say, oh, on line 8, you tried to use a variable that's been moved. Sorry. What are you supposed to do with that? Well, open up the code and sort of trace backwards what went wrong. But the Rust compiler gives you all 3 steps that led to where we are. It tells you, okay, the type in question is not a copy trait one, so it has move semantics. It tells you where the move occurred, and then it tells you where you tried to use the value that you moved. So, pretty nice. If every compiler were this helpful, it would be a lot easier to get started with programming. Unfortunately, not always the case. Now, move semantics makes sense also when returning a value from a function. In the example here, make string function allocates a string and returns it. And so ownership transfers from the function that created the string to the caller. That makes sense. It would cease to exist when the make string function goes out of scope, when it's no longer needed, when it doesn't exist anymore after it's been called. So transferring that return value is sensible. Ownership is transferred by the return statement, and it's set to the return value of this function. And so it is assigned to S1, and everything is fine. Wait. Come back with that. It works in the other direction too. Passing a variable as an argument to a function results in either a move or a copy based on the nature of what you're passing. If it's a copy type, then of course it's a copy, so we're just passing an integer, then we take a copy of it. But if it's a string, that's a move. You can have them back by returning those variables at the end of the function. If it explicitly returns it, but maybe that's not actually what you want. Maybe you don't want to actually give this away. So in the code example here, main creates a string world and then calls function use string that transfers ownership to the function being called, and then after that you can't use it anymore because use string prints it out and then has no more use for the string, so it drops it. That's fine if you really didn't need that string anymore, but maybe you wanted it back. So there are 2 things that would work in this situation. One is you could clone S1. You could, when you're calling use string, call it with the argument s1.clone. That would work. That might not be ideal because you're making a copy of it, but okay, we can do it. Or you can have it returned by the function in question, so it returns the value after it's been used by putting a return statement at the end of use string that gives you it back. If you are returning multiple things, that gets a little bit clumsy, because at the end of your function you are returning several different values, and sometimes you don't want that anyway, because the return value should be different from what was passed as an argument. So maybe what you actually want is the ability for a function to borrow it. Could we do that? Well, we'll find out soon enough. Okay, we'll come back to the subject of borrowing in a bit. But here's a question that I want to think about just for a minute, which is, do the rules work? We've learned about the 3 rules. They seem straightforward. We'll go into some more detail about things in future lectures, but with a stronger understanding of the rules, can we ask ourselves this question? I think we can. And there's no point in having the rules if they don't accomplish the goal. So let's just think about some things that could happen in a C program. So before we get there, of course, we will learn to eventually break some rules, and when that happens, things don't necessarily have the same guarantees, but just using the rules. Do we avoid memory leaks, which is to say failing to deallocate memory? Yep, we don't have that problem because memory is deallocated when its owner goes out of scope. So the compiler chooses when it is appropriate to deallocate that memory. There's no need for you as the programmer to explicitly declare free or delete, which you could forget or do at the wrong time. Same thing with double free. Again, this does not happen because deallocation happens when the owner goes out of scope and a particular piece of memory has one owner. Use after free does not happen either because a reference is no longer valid, results in a compile time error. If something has been dropped, you can't use it anymore. The compiler will tell you it ceased to exist. Sorry, it's not there. Accessing uninitialized memory. This will be caught by the compiler. The compiler will check whether memory has been initialized before you try to use it, which is something that we sometimes forget in C, because malloc will create it, but not necessarily initialize it. And stack values going out of scope when a function ends. This one's a little esoteric, but it happens sometimes. If you are passing data from one thread to another, in a C program, you use pthread create, as you will have seen in either the previous course or in the review slides, or review notes, I should say. And it could happen in that scenario that you, instead of passing like a pointer to some heap allocated memory, you say, address of this stack allocated memory. The compiler won't object because it's valid. A pointer is expected, and by using the address of operator, you did in fact provide a pointer. However, the stack allocated memory does go out of scope when the function that it exists in ends. So when that happens, you can in fact end up passing some memory that's not really valid anymore to another thread, and the other thread doesn't know that because it gets whatever it has. That will not happen in Rust because the compiler will require that data is moved or copied before it goes out of scope, and will restrict you from doing things that are bad. Now, there's no free lunch, and to provide a somewhat more balanced view, Rust obviously does not solve every possible programming problem that could ever exist. I think that it solves memory management well, and I wouldn't say that it requires more of you as a programmer than other languages would. I think it asks you to invest your effort at compile time and not at debug time. And as I keep saying, I am of the opinion that debug time is much more expensive. Fixing the compile time error is a lot simpler and cheaper in terms of programmer time and possible impacts on your program than trying to debug something that goes wrong in your production code. So I think it makes a certain amount of sense to try to move as much upfront as possible when it is least costly to fix. Now, there are some downsides to consider, and static typing is one of those. Rust is kind of strict. There is a saying in New Zealand, she'll be right. It's a little hard to explain, but it is a situation or object which is not perfect, but good enough to fulfill its purpose. So says Wikipedia, so it must be true. And static typing in Rust discourage this kind of point of view. The code really does have to satisfy type safety and memory safety before it will compile and before it will run. This will occasionally make you a little bit frustrated because you are certain that things are correct and the compiler says, I'm not convinced. And this can end up with a little bit of frustration or haggling or trying to trick the compiler. If you are ever saying to yourself, what I want to do is trick the compiler, you should probably rethink that, but you can see why it might be a little tempting under the circumstances. The Rust ecosystem is not necessarily fully fleshed out as compared to some other languages. Rust does come with a package registry. It's called crates, and having a package manager in some sense is better than other languages. In C++, there's really no such thing. You'll use a dependency system, Maven, Makefiles, Gradle, something. To compile your code, but some libraries don't exist in Rust. You can interface with foreign functions, foreign in the sense meaning written in a language other than Rust, and we'll talk more about that in an upcoming lecture. And there are certain costs and penalties associated with doing so, and one of them is because they're not written in Rust, they can have all of the problems that non-Rust code has. The last thing to mention is the Rust compiler. It can be kind of slow on certain large code bases. There has been a fair amount of work done in optimizing the compiler and improving its performance, to the point actually where we're going to talk about that as its own topic in the course. But compile times being slow is kind of a known issue for Rust. Anyway, with our introduction to Rust sort of in hand, this gives us an overview of the basics. It should be enough to start writing some code and doing some exercises. However, in the next lecture, we will talk about things like ownership in a little more detail, especially in the context of borrowing and other things that are a little more complicated than just transfer of ownership. All right, till the next lecture.